The second spectral parameter, which is called quadrupole splitting or nuclear quadrupole moment or nuclear quadrupole interaction. So what exactly this quadrupole or quadrupole moment? Now we will discuss about quadrupole moment first. Quadrupole splitting or nuclear quadrupole interaction can be denoted as Q, simply Q, or EQ, where E is the electronic charge. It is a measure. It's a parameter. A quadrupole moment is a parameter or a measure that describe the deviation of a nuclear charge distribution from spherical symmetry. Let me explain about that. The nuclear charge is distributed in a spherical manner. Okay, nuclear charges are distributed in a spherical manner. So, if there is any kind of disturbance comes, the nuclear distribution in the sphericity or the spherical manner will be tilted or deviated. This deviation can be measured in terms of quadrupole moment. So, certain nuclear, the nuclear with the spin quantum number greater than or equal to 1. It can be integral and half integral, but not equal to half. Okay. The spin quantum number can be integral or half integral, not equal to half. That in simpler time, I greater than or equal to 1. So nuclear with the spin quantum number can integral or half integral value, but not equal to 1 by 2, also known as quadrupole nuclear. So quadrupole moment is a nuclear is a measure, is a parameter of a nuclear which describe is a measure of the deviation of nuclear charge distribution from spherical symmetry. How? What's the reason? This is either because of the presence of an external electric field or the presence of an unsymmetrical electronic distribution around the nucleus. See, if this is the spin of a nucleus, the nuclear charge is distributed in a spherical manner. If the electronic distribution, if the external electrons or the inner electrons are distributed around the nucleus in an unsymmetrical manner, let us consider the example. In the case of an iron 57 MÖSSBAUER spectroscopy, consider an iron complex. Here, the FeCN6 formations. This iron is having Fe2 plus a D6 coordination number. So, cyano group is coordinated in an octahedral manner without having a symmetrical manner. So, there is no quadrupole shifting because the nuclei is in a symmetrical phase. The ligands are arranged symmetrically, right? 6 cyano groups ligands are arranged symmetrically around the metal ion Fe. But when one of the cyano group is replaced by another ligand, the symmetry fails. The symmetry disturbed. Okay. So as a result of that, unsymmetrical spinning of nuclei occur. Unsymmetrical nuclear charge distribution occurs. This creates a quadrupole moment, and this quadrupole moment split the nuclear transition between the absorber energy levels. This is the reason quadrupole splitting. Let me repeat with the example again. In the case of an iron complex FeCN6, due to the presence, so the ligand electronic distribution is symmetry because all the ligands are the same. If one of the ligand is replaced by another ligand, the electronic distribution is entirely different in that ligand also. So the cyano group is replaced by a nitrosyl group, nitro group. So this will disturb the symmetrical distribution of electrons around the nucleus of iron, and as a result of that, quadrupole splitting occurs. This quadrupole splitting causes the splitting of energy levels of absorbent nuclei into two. So before moving to discuss on this energy level diagram, we have to understand certain more concepts and terms related to quadrupole splitting. The first and very important is electric field gradient. You all know that quadrupole moment and the spin quantum number of nuclei with the greater than half, 1 by 2, They are also known as quadrupole nuclei. This quadrupole nuclei interact with electric field gradient. What exactly electric field gradient? Due to the presence of the ligand and the non-bonded lone pair of electrons present in those ligands and the internal electronic distribution around the nucleus, these electrons create an external electric field. So the rate of change of this electric field, the rate of change of electric field in each direction is called, the rate of change of electric field in each direction is known as electric field gradient. Okay, electric field gradient. Rate of change of electric field in each direction is called electric field gradient. This quadrupole nuclei interact with this electric field gradient, forming nuclear quadrupole coupling constant. That means in mathematically it can be expressed as EQ or simply Q. EQ, E is the electron charge, Q is the quadrupole moment. Interact with the electric field with the charge Q, EQQ, which is called quadrupole coupling constant. This electric field gradient is a vector quantity, is a direction dependent, and this is formed due to the symmetrical distribution of non-bonding electron or nuclear electrons or ligand electrons with a different character. Ligand electrons create this electric field gradient. Now we move on to the energy level diagram. Due to this quadrupole moment and coupling with electric field gradient in each direction, the nuclear transition, the energy levels of the nucleons, the nuclear energy level splitted. As a result, the 3 by 2, the energy level 3 by 2 gets splitted. You all know that quadrupole splitting does not affect half. So the ground level, the ground quantum number I is equal to spin quantum number does not be affected by the quadrupole splitting. Whereas if I greater than 1 by 2, it can be integral or half integral 3 by 2 from 1 to across. So 3 by 2, the excited level gets splitted into 2. Okay, the excited level gets splitted into 2. So and splitted into plus or minus 3 by 2 and plus or minus 1 by 2. So the source nuclei when emitted the gamma radiation, as a result of this quadrupole splitting, the excited spin quantum number 3 by 2 splitted into 2. 3 by 2 and the difference between the two sub energy level is known as quadrupole splitting energy delta EQ. Okay, delta EQ, and the corresponding spectra comes to a doublet. Corresponding spectra provided as a doublet. See, this is the central 0 point, and there is two troughs. Two peaks are observed, two troughs. The difference between the two troughs gives the value of the energy, the quadrupole splitting energy. So this is the most important point you should note. Because of the presence of electric field gradient and the unsymmetrical distribution of electron. Unsymmetrical distribution of electron we have already learned that due to the presence of ligands with a separate electron distribution. We have already learned that FeCN6 4 minus and FeCN5NO 2 minus. In both these cases, in the first case, all ligands are same in the same electronic environment, the symmetrical environment. So there is no splitting. Only single spectra will come. But whereas when one of the cyano group replaced by NO, there is two ligands. Ligands having separate, unsymmetric, separate electronic distribution, though asymmetric in nature. As a result, the energy level diagram split into two. That will also result in the spectra. We obtain a doublet. So this is the quadrupole splitting. Now we will discuss the mathematical expression of quadrupole splitting and to find out the quadrupole splitting energy. For that, we have to apply the postulate of quantum mechanical concept. According to quantum mechanics and based on the postulates, every physically observable property can be expressed in terms of an operator. An operator which changes with respect to variables, multiple variables, either in x, y, and z direction. So the quadrupole moment is expressed in terms of Hamiltonian operator HQ, and which is given as EQ QZ divided by 12 into 3IZ square minus 15 by 4 plus eta into IX square minus IY square. What exactly this data? This is the electronic charge. Q is the quadrupole moment. QZ is and QZ is a principal component of electric field gradient EFG. Electric field gradient is the rate of change of electric field in a given direction, and this is the electric field, the component, the principal component of electric field gradient in Z direction. IZ, IX, IY are the spin quantum number, nuclear spin quantum number in X, Y, Z direction, and eta. Eta is equal to Qxs minus Qyy divided by Qzz. Qxs, Qyy, Qzz are the principal component of electric field gradient in X direction, Y direction, and Z direction. The derivation is not required now, but you should understand the components of this Hamiltonian operator of quadrupole moment. And this eta is called asymmetry parameter. Due to the asymmetry of electronic distribution, this quadrupole splitting happens. So this gives the asymmetric parameter constant. And what exactly the theoretical concept of theoretical mathematical equation of quadrupoles splitting energy delta EQ is equal to EQ QZ divided by 2 square into square root of 1 plus eta square by 3. This QZ are the principal component of electric field gradient in Z direction. Eta is the asymmetric constant, asymmetric parameter, which is expressed as Qxs minus Qyy divided by Qz. Okay. So this is the mathematical expression of Hamiltonian quadrupole moment, which is expressed in Hamiltonian operator, and this quadrupole splitting occurs, split the energy level diagram of I equal to 3 by 2 only, because the quantum number, the spin quantum number must be greater than 1 by 2. So it does not affect any splitting to the quantum number a ground state level I equal to 1 by 2. Let us consider the example. In the case of ion complexes with the Fe2 plus, where Fe2 plus exists in low spin and high spin states. In the case of low spin state, all the electrons get paired. So see, Fe2 plus is having D6 coordination number, right? D6. So in the normal course, 1, 2, 3, 4, 5, and 6, right? This is high spin case. In the case of high spin case, the difference between the energy, the delta EQ, the difference between the two troughs is very high, and the value will become 3 mm per second. Whereas if these electrons get paired, what exactly happen? 1, 2. If the electrons get paired with the ligand electrons, or it get paired, the difference between the quadrupole splitting energy, the difference between the two troughs will become small, 0.3 millimeter per second. So this quadrupole splitting value can be used to find out the oxidation state of electron and nuclear, oxidation state of nuclear. Second, the spin state, whether it is low or high spin state of the of nuclear present or not. And the third is coordination, the type of coordination number and type of ligand present, and what kind of interaction, what kind of electronic interaction present in that ligand with the complex, every details. These details can be elucidated from quadrupole splitting of MÖSSBAUER spectra. Okay.